In the 1950s, when the first nuclear power plants were beginning to be built in the United States, the original equipment was comprised of physics-based systems.
There were many problems in physics to be solved. This required reactive physics analysis and thermal and hydraulic calculations.
Those systems did what they were supposed to do, and people were satisfied with the maintenance activities required, the upkeep activities required. But now as time went on, those systems have become hard to maintain. The basic components within those systems have now become unavailable. And almost the only choice on the market is software-based systems. They were more expensive, they took longer to verify that they operated correctly, they had vulnerabilities to cybersecurity attacks. It was clear that there may be an opportunity to do something different.
EPRI is a global nonprofit research and development organization that really focuses on benefit to the public. There is just this drive around the entire world to accelerate technology towards affordable, reliable, and clean energy for the entire world.
Maybe we need to rethink about why software has to be the center of everything. There can be other ways of doing it, and we've proved it in the past. And we can bring those ideas to the future and reimagine them in ways that would cure the obsolescence problem, but also what used to fill rooms of clunky hardware, we can make it very small. We can make it very reliable. After EPRI received funding to pursue this endeavor, we needed to find a partner that had the resources and team to bring it to life.
I met Matt at a conference and we started talking, and he had these ideas about building what we call verifiable systems.
The goal of our project was to create alternate I&C architectures. And we really had two compelling pathways. One for an electronics-based, software-free idea, that would be SymPLe, and the other was the NEMs and MEMs relay projects. And so we decided to do both.
When we sat down and discussed the ideas in detail, I knew this was the perfect fit for the faculty and researchers at VCU.
These are millions of dollars that are invested into these laboratories that allows us to design and test different microelectronic systems, which may not be readily available to every company. At the other side, the companies can provide us expertise for real-life problems, the real-life examples, the real-life challenges that require multidisciplinary research that we hope to accomplish with our faculty in those partnerships.
The unique skill sets that VCU brings, along with the credibility, the expertise, and the engagement that EPRI brings, really drives that partnership into developing a technology that can be broadly applied within the industry.
I've been doing this 25, 30 years. This is the first time that I've experienced a true collaboration where we equally contributed to this fruition of this technology. Rarely happens, and it did happen in this regard.
If you're willing to think differently, you can look at the past for inspiration like we have. You can discover things you didn't know before and create something new, something better for its time.
With today's advancements in technology, the possibilities are truly endless. In today's nuclear power plants, complex processes are conducted under the careful supervision of both man and machine.
When the capabilities of nuclear energy began expanding, the industry ran into several challenges, upgrading their analog equipment to digital equipment. Because of the complexity in these systems, it really became very difficult for certifiers and regulators to gain a high level of confidence in the safe operation of these systems. EPRI came to VCU with this idea, is like, how do we make these automation or instrumentation and control systems less complex for the sake of assurance, so we can actually verify that a platform is doing what it's supposed to do.
What we need to look at is how to constrain these types of complexities for the positive purposes of making them more reliable, making them more safe, making them more secure, to make systems that people can trust. SymPLe is an architecture built to be understandable, verifiable, so that you can have this justifiable trust placed in it for the high integrity applications.
SymPLe is an architecture overlay. that can be implemented on custom substrates as well as an FPGA or an ASIC.
Think about it as like your CPU in your computer, except without the software. You have functions totally implemented as hardware. So we can do anything that software can do, but we're doing it with electronics at the fundamental physics level.
You can do tasks that you would normally do on something like a processor without all of the variance that leads to unpredictability of what happens on a CPU software.
The way that we design SymPLe is we have a set of complexity-aware rules, meaning every decision we make, we want to make sure it lines up with more efficient and effective testing, so that essentially what we try to create is this body of evidence that this thing actually does what it does without any side effects, without any gotchas, without any surprises, because that's what you want for safety and security. Think of the number of what we call test vectors that you have to run for any particular function. You might have hundreds of test cases that you have to do to essentially verify that functionality. With complexity-aware design decisions in place, you're down into dozens of test vectors. Testing is time, time is money. So if you reduce your testing and still have the same effectiveness, it's a cost-effective solution. And it's software free. That's the secret sauce of SymPLe.
The general public is still skeptical about some of the innovations on display. That's why scientists are coming together to work on the impossible, creating technology that is both effective and safe for every industry.
EPRI has really been good at bringing us potential problems seen in nuclear power and then also potential innovative solutions for those problems. The most exciting part of all of this is just doing something new and solving problems out there that other people have not been able to solve thus far.
What I've enjoyed the most about these projects is really seeing the excitement of the researchers when they're given an opportunity to think independently, on a discovery mode, really stretching themselves and how they think about things, and and the pleasure they get from that. And that's been very rewarding for me.
It requires a lot of forethought and planning. My work on SymPLe has been a test, making sure that we're building the right thing the right way.
We want to bring this technology to the entire nuclear industry. We think of it as intellectual property that basically somebody can pick up and develop systems on, integrate it into their in-house product. And that's our strategy right now, is early commercialization to try to deliver this to the nuclear industry.
The SymPLe architecture has applications in any critical industry, especially one that values reliability and cyber immunity.
SymPLe offers a different sort of protection and control in a variety of different applications, not just nuclear, medical, avionics, transportation, military, automotive, and aerospace.
SymPLe in particular could be used in medical devices. It could be used in voting machines.
There is a similar type of excitement in these companies about what they see as the promise of SymPLe, primarily due to those complexity-aware design decisions we make at the beginning. Everything about SymPLe is about making it more efficient and effective testing from the very beginning when we think about the requirements to the very end when we put it on hardware.
The more systems that we can get SymPLe into, the more we can learn about how it stands the test of time.
In order to optimize output, speed, and safety, engineers have worked tirelessly to reduce the size of today's nuclear technology, with the hopes of creating higher efficiency at a much smaller scale.
When we began this partnership, we wanted to address two challenges with relays in nuclear plants: safety and size. The idea is to reinvent relays on a micro scale, something with a small package, small footprint. So if you have relay logic, which is a technology that goes back decades and decades, predating integrated circuits, let's take that system and apply that to the nuclear power industry.
In this project, we are focusing on very small scale, small footprint. Now, to micro scale relays, you can put hundreds, thousands of these things in a small chip and turn them into an integrated chip that can be configured into performing any control action. Most instrumentation and control systems are based on software-based digital systems. So we are developing non-software physics-based technology using electromechanical relays, electromechanical switches based on nano to microscale electromechanical systems made of silicon material system. We use conventional photolithography to write a pattern onto the silicon-on-insulator wafer. After that pattern is written, we etch the silicon material at the very top of this to form an electromechanical relay structure on this wafer. You can fabricate hundreds to thousands of these electromechanical relays on a single wafer. They can be interconnected to perform a certain control action, very similar to an integrated circuit. There's an oxide layer that is underneath this silicon material. We remove the oxide layer, which releases the moving part of the electromechanical relay. The last step is metallization of this structure, and metal provides our connection to the outside electrical signals. You apply an electric field and you perform an electromechanical action of what we call a cantilever that provides the switching action.
It's all the high-resolution lithography that allows you to make things really, really small. If you talk about the size and the scale of these types of devices, and if you think about a human hair is on the order of 100 microns in diameter. These things are a fraction of that. Some of the relays go from the 100 micron scale, and then other ones go down to just a factor of 100 times smaller than that, so just a small fraction of the size of a human hair. Over the decades, the ability to pattern things at extremely small scales has improved many times, so we're just taking advantage of integrated circuit fabrication techniques to make essentially little micromechanical devices that are similar to the relays of the 1940s and 1950s. It really makes this technology extremely inexpensive to implement.
It comes with significantly reduced maintenance costs, therefore lower cost of ownership. It is not software-based, therefore it is immune to cyber exploits and software errors. People should be interested in a reconfigurable system for their needs that is based on physical electromechanical relays, no software. That is a potential game changer for a lot of applications.
Given the nature of the materials being handled in nuclear power plants, safety is the most critical priority. Luckily, technological advancements are helping engineers perform their duties with minimal risk.
If you look at the non-software solutions used in the nuclear power plants currently, they use macro-scale electromechanical relays. Thousands of those relays take out the whole room. They require a lot of power, so they generate a lot of heat, and they require high maintenance costs. For next-generation nuclear reactors and small modular reactors, small footprint comes with several advantages.
You don't want to make something small just for the sake of make it small. It's always field should perform some function. EPRI wants some very robust safety solutions which allow safety control of a nuclear plant environment.
What the micro and nano relay technology brings to the table is environmental hardening. In other words, very radiation hardened, even very close to the neutrons in a nuclear reaction. It can operate in very high temperature environments. It's very immune to electromagnetic interference, more so than electronics, which allows it to operate in very harsh EM environments. So you're talking about being able to implement logic in a harsh environment, also environments that have very low power, because these relays really don't draw a lot of power to do what they do.
You can interconnect these relays, make them perform certain logic actions. So you turn them into an integrated chip. You take the silicon wafer, slice them into small chips, mount them onto a chip carrier, which turns into an integrated circuit. Then anybody can take that integrated circuit and put them in their application with very small form factor to perform any control action that you need for a control system required for any safety-critical, safety-related environments.
You're making tiny little relay systems the same scale as integrated circuit chips, And so you tend to package them and employ them in a similar way to where you can put them in the same types of packages that are used in integrated circuits. So you can kind of integrate them into already existing technology for whatever system you need to employ.
It's entirely possible to envision a future in which the technology you've seen today will be adapted for use in our businesses, in our hospitals, in our automobiles, and even in our homes.
What we've discovered in pursuing this research and development is that we can think differently. We can try to solve our problems thinking more about how to solve a problem without constraints than trying to fit the problem into an existing solution.
Having a configurable logic solver based on nano microelectromechanical relays, it is going to be a game changer. This idea was new. So we introduced this idea, but the procedures are already out there. So it makes our idea very easy to push through mass production. In terms of nano and microelectromechanical relays, we are at initial stages of pushing this through commercialization. Nobody has done this thing before. So imagine an integrated circuit that comes to you. You'll be able to configure this to perform any control action. Particularly for the safety critical applications, people should be interested in a reconfigurable system for their needs that is based on physical electromechanical relays, no software.
There's a similar type of excitement in these companies about what they see as the promise of SymPLe in their own product lines. When we think of backup systems, which have to be highly safety critical but bulletproof, SymPLe fits into that category. So you can think of backup control systems on aircraft. We see applications like that for SymPLe in many different type of domains.
One of the advantages that we have is that we're using fabrication techniques that go along with the integrated circuit industry. It could be something that you could incorporate into existing chips anywhere where you need sort of a backup safety system. So it really makes this technology extremely inexpensive to implement.
We see very broad application of this technology across the board. That can be within different types of energy supply and different types of power plants, but it could also be in different industries altogether, well outside of energy. We are at the point where we are ready to start doing further testing, looking for different partners who want to take this technology, help us bring it to market, commercialize it, and get it used within industry. Help us identify true use cases to apply it broadly across the industry. It could potentially be a game changer. It could potentially have a huge impact on the flexibility, the efficiency of nuclear power as we move forward. And nuclear power is such a very, very important part of what our energy economy has to look like in the coming decades.